discuss about the discrete wavelet transform as applied on the images. So, DWT as applied on the images, and also the way we are going to encode the DWT coefficients. So, DWT on the images and its encoding. This will be the topic that we are going to cover today. Now, before now, I mean, in the last class we were discussing about the way the discrete wavelet transform is applicable on the images. Okay. Now, as we had seen that we can apply the concept of the one dimensional discrete wavelet filters, okay, applicable into two dimensional way, so that one can apply it on the images, because images being two dimensional signal. So, essentially what we have to do is I mean, in a block diagram form we can summarize it like this, that if we start with a scale, let us say that we start with a scale j plus 1, in that case it is I mean filtered image, if we take as W phi j plus 1 and with m and n, where m and n are the indices in the row and the column directions. Okay. So, m and n, so m is the row index and n is the column index, and j is the j plus 1 will be the starting scale. Okay. So, this is the scale. Okay. And what we can do is that from W phi j plus 1 m n, W, the suffix phi indicates that it is the scaling function. I mean, it is after application of the scaling function, that means to say that it is the low pass filtered version of the signal. So, meaning that when we are applied on the two dimensions, then the subband that we are getting by filtering the image as low pass filtered along the rows and low pass filtered along the columns, that means to say the LL subband, the picture which we had shown in the last class. Okay. If you recall that what we did in the last class was that after applying the discrete wavelet transform on the images, okay, we will be essentially getting 4 different subbands which we are designating as the LL, HL, LH and HH, okay, these 4 subbands respectively, where LL is the low pass filtered. Okay. So, essentially this is W phi. So, you can say that W phi to start with, W phi could be the entire image itself. Okay. But as we are going to show that such kind of application can be made to any scale, that means to say that once we obtain the subbands, okay, we can iteratively partition the subbands which we already obtained. Okay. So, we are going to show that anyway. I mean, first let me complete that what I was trying to tell you, that means to say that if W phi j plus 1 m n is the starting signal, then this starting signal we are passing through 2 filters, okay, and one filter is what we are calling as H psi of minus n. Okay. Now, basically n is the index of the column. So, definitely this is the filter that we are applying along the columns. Okay. Now, H psi means it is the wavelet filter applied on the columns, and likewise we also have to apply the scaling filter which we indicate as H of phi minus n, that will be the scaling function that will be the scaling filter or the low pass filter that we will be applying on the signal. Okay. Now, this is applied along the columns. Okay. Now, what we do is that because we are splitting up the signal into two essential two bands, all right. So, it is I mean, one is the low pass filtered version and the other is the high pass filtered version. This is the high pass filtered version, and h of phi filtered by h of phi gives us a low pass filtered version of the signal. Now, whenever we are splitting up into two subbands like this, in that case the band, or rather to say the bandwidth of the signal, okay, the spatial bandwidth of the signal essentially gets halved in each of these subbands. Okay. So, as a result, what happens is that we will be getting redundant samples, and one does not lose any information by having by throwing out the alternate samples. That means to say that having a subsampling by a factor of 2. So, what we have to do is to apply, I mean, both on the H psi filtered image and also on the H phi filtered image, we have to apply a subsampling by a factor of 2. Subsampling means that we, I mean, out of 2 consecutive samples, we pick up only one of them and discard the other. Okay. So, which means to say that if we start with n number of samples over here, in that case at the output of each of these filters we will be having n samples at the low pass filtered as well as the high pass filter, but individually their bandwidth is halved. Okay. So, out of these n samples only n by 2 samples will be required for both low pass filtered and for the high pass filtered version. Now, how do you get n by 2 samples? You have to do a subsampling. You have to throw out the alternate samples. So, this is a subsampling by a factor of 2 which you are doing in both these directions. And then this subsampling you are doing along the columns, n being the column index. So, when you are applying a column filter, okay, or rather the wavelet filter along the columns, then subsampling also is along the columns. Okay. So, you do a subsampling by a factor of 2. Now, after that what you do is that once you subsample this, okay, along the columns, you can now apply the one dimensional filters, okay, along the rows. Okay. So, what you do is that this signal you can split into 2 other bands. Okay. One band you call as H psi, and this time we are going to call as H psi minus m. Okay. The index m is used for the row. Okay. And here we are going to call it as H of phi, that is the low pass filtered version, H phi of minus m. Okay. So, after the column filtering we are applying one low pass filter along the row and one high pass filter along the row. This is the low pass filter along the row and this is the high pass filter along the row. Now, individually again each of these subbands will contain half of the samples. So, what we have to do is to subsample by a factor of 2, just like the way we did subsample in the in the direction of the columns. Here we have to do a subsample in the direction of the rows. Okay. So, what we do is that individually these 2 channels we have to do the subsampling and we will be getting these 2 outputs. Okay. So, this we are going to call as W psi J M N, and this is, and just look at the nature of this signal. This signal we are deriving by high pass filtering along the column and high pass filtering along the rows. Okay. So, which means to say that it is extracting the high pass along both rows and columns, which means to say HH. Okay. Basically, HH subband is being referred to over here, and high pass filtering extracts the edges. So, this is extracting the diagonal edges. Okay. So, we are going to indicate this as W psi with a superscript D, okay, because it is extracting the edges along the horizontal as well as the vertical, which means to say that it is extracting the diagonal edges. So, W psi superscript d j m n. So, from the scale j plus 1 we have got into scale j, right. Now, what is this one? This one is going to be, I mean, along the columns there is a high pass filtering, but along the rows there is a low pass filtering. So, because along the columns there is a high pass filtering, we are extracting which edges? The vertical edges. Okay. So, we are going to call this as W psi superscript v j m n. Okay. And for the low pass filtered signal along the column, okay, we can apply the two filters similarly. We can apply H psi minus m and we can apply H phi of minus m. For each, so individually, I mean by very similar argument, we have to do subsampling by a factor of 2, right. And what we have over here is just the opposite of what we had for W psi superscript v. Why? Because along the columns it is low pass filtered and along the rows this is high pass filtered. Okay. So, that is why this channel we are going to call as W psi, but with a superscript h j m n, and this one is going to be what? Low pass filtered along the rows, low pass filtered along the columns, low pass filtered along the rows. So, this is the LL subband, or rather we are not going to call it as W psi, we are going to call it as W phi j m n. Now, look at something interesting. What was our starting point? Our starting point was W phi j plus 1 m n, and in this case what have we got? W phi j m n. So, what is the difference between this and this? Only that j plus 1 is changed here to j, all right. So, we have come one scale down. Okay. We have come one scale down means that we have effectively lost the resolution by a factor of 2 along the horizontal and along the vertical directions, right. So, you see, I mean the picture that we had shown in the last class. So, individually, because we are doing subsampling by a factor of 2 along the rows and also along the columns, we are effectively doing a subsample by a factor of 4, right. So, 1/4 of the samples. So, LL subband contains 1/4 of the total number of samples which are there in the image, and likewise every subband is containing 1/4 of the total number of samples. So, we are just indicating, I mean the way of representation like this means that in this part or in this quadrant we are accommodating all the pixels which are basically the LL filtered version, which means to say along the rows low pass filtered, along the columns low pass filtered, that type of signals we are putting into the LL subband. Now, essentially what we are getting is that individually these 4 bands, now these 4 bands individually can be partitioned or analyzed further. Okay. We can take up the LL subband, we can take up the HL, LH or HH, any of these 4 subbands we can pick up, okay, and we can do a similar partitioning, okay, or similar sub partitioning, okay, like the way we did for the original signal. So, original signal partitioning we got this 4. Now, let us say that we take up this HL subband. So, we will be partitioning this HL subband into 4. Okay. Here there will be the LL subband within this HL, Okay. This will be the HL within this HL, this will be the LH within this HL, this will be HH within this HL. Okay. And then any of these subpartitions also can be analyzed. Likewise, LH can be analyzed, HH can be analyzed, LL also can be analyzed. Now, which one is normally taken out of these 4 subbands? Now, as I have told many times that images are generally very rich in the low frequency content. So, whenever we are doing signal analysis on the images, okay, essentially what we try to look for is that we do the analysis further, okay, on the low pass filtered version of the images. So, LL we have already got one low pass filtered version. Okay. So, it is the, I mean, if we look at the image, we will be seeing that as if to say that the original image has been squeezed to a 1/4 size image and put into the LL subband. Okay. And most of the, I mean, the richest information, okay, out of all these 4 subbands, you will find the maximum information content within this LL subband only. So, logically what we should do is to partition this subband, and mathematically also it is very easy, because now having obtained W phi j mn from W phi j plus 1 mn, I can use this W phi j mn, okay, use that as the starting point to the next one and obtain 4 subbands over here at the j minus 1 scale. So, here I will be obtaining W psi j minus 1, W psi v j minus 1, W psi h j minus 1, here I will be obtaining W phi j minus 1. So, if I analyze LL subband, essentially what we are going to get is something like this, that this was our original image size. Okay. We split up into 4 subbands, okay, and let us say that we keep the HL, LH and HH intact as it is, but we analyze the LL subband further. So, that means to say that we will be obtaining 4 subpartitions of this LL subband. Okay. So, which means to say that here I will be getting one LL subband, but this LL subband we will not write as LL, we will use a subscript, let us say a subscript 2 we use, 2 indicating that this is the second level of decomposition, right. So, this is LL2, this will be HL2, okay, this will be LH2 and this will be HH2, and just to keep the consistency we mark HL as 1, LH1, HH1. So, where the number that I am writing in the subscript essentially indicates the level of partitioning. So, totally we now have 7 subbands as you look at it, right. There are 7 subbands, 4 subbands at level 2 and 3 subbands at level 1. Okay. Now, again what happens is that individually any of these 4 subbands can be analyzed, okay. And again we will be finding that it is the low pass filtered version which contains the maximum number maximum amount of signal. Okay. So, LL2 will be richest in the information as compared to the HL2, LH2 and HH2. So, it will make more sense in partitioning this LL2 subband further. So, we now decide to partition LL2, partition it into 4 subbands. Here this we will be getting as LL3, this we will be getting as HL3, this will be our LH3, this will be the HH3. So, we have done come one more step further, that means to say that this is a typical 3 level decomposition, okay. And nothing prevents us from making a fourth level of decomposition or fifth level of decomposition. So, I can go and go further and further down. So, which means to say that actually what is the physical concept of the scale? What was our highest scale? Highest scale was the original image. Now, original image contains the maximum resolution, okay. And after the first level of decomposition, every subband is containing 1/4 of the resolution, okay. So, there is a bit of coarseness which we have incorporated after the first level of decomposition. Then second level further coarseness, third level further coarseness, like that we are going from the finer domain to coarser and coarser domain of analysis. Okay. Essentially, what is the purpose? Remember what we talked in the beginning, that the whole objective of doing the wavelet analysis is a localization, and in this case we are talking about the space frequency localization. Okay. We want to know that at which spatial location, okay, or within which spatial location range we are going to have the higher frequency component, and at which spatial location we are going to have lower frequency component, and like that. Okay. So, in order to have that kind of analysis, okay, or space frequency localization, okay, this sort of a partitioning is definitely going to help us. Now, this way of partitioning the LL subband, okay, and obtaining the further subbands out of it, this method of partitioning is called as dyadic partition. Okay. Now, commonly dyadic partitioning is followed in the image because of the reason I told you, that the images are rich in low frequency content, and that is why this dyadic partitioning scheme, okay, where the LL subband only will be decomposed into further and further coarser levels, that is adopted. Okay. So, this is the total scheme of the dyadic partitioning, and although I mean it is not mandatory that you have to do dyadic partitioning only, because individually any of these subbands you can analyze. If it so happens that your image is having rich high frequency contents, okay, it is having a rich HH band contents, you can analyze the HH band and obtain and extract some further analysis. You can do further analysis on that in order to derive your signal. So, this is very widely used, and having known this, so what we did essentially is that how to apply the wavelet on the images. Now, the same thing one can mathematically write down like this, that let us say that we take the image function to be S n1 n2. Okay. So, and we take the image size to be capital N1 by N2. So, this is the size of the image. N1 by N2 is the size of the image, and the intensity function is indicated by S n1 n2. Now, what we are doing in the wavelet transform, basically this S n1 n2 which is in the spatial domain will be transformed to the wavelet domain. So, what we obtain? So, basically we will be obtaining two signals, one is the scaling filtered signal and the other will be the wavelet filtered signal, and we can write down the mathematical expressions like this, that W phi, okay, if we apply the wavelet filter at scale J0, let us say. Okay. So, we are writing it as W phi, okay, J0, and as the index we write as K1 and K2. The index in the N1 along the N1 direction we are writing as K1, and the index along the N2 direction we are writing as K2. The reason why we are using the indices as K1, K2 instead of using N1, N2 is just to make a separation, that N1 and N2 we are using for the image domain index, and K1, K2 we are using for the wavelet filtered domain index. Okay. So, W phi J0, J0 being the scale, K1, K2 will be the wavelet filtered image, and this can be written as, I mean, a general form of two dimensional discrete wavelet transform would give us 1 upon root over N1 N2, and because it is a two dimensional thing, we will be having a double summation, and the wavelet is being applied, in this case scaling filter of course, will be applied to the image signal which is S N1 N2, right, and the index will be N1 going from 0 to capital N1 minus 1, and N2 will go from 0 to capital N2 minus 1. Okay, this is S N1 N2, and then we have to multiply this S N1 N2 by phi J0 K1 K2. Okay, this will be the filter, and this filter will be applicable on N1 N2 at the position N1 N2. Okay. So, because N1 and N2s are varying over here, this will be applied at the different positions, because at every point of the image we have to apply the corresponding filter, and the product of this and then added up, that gives us the W phi. And similarly, we will be obtaining the W psi, okay, J0 K1 K2, but mind you, we are applying the, I mean, for the low pass filter we are having only one subband, okay, whereas for the high pass filter we are having 3 subbands. So, essentially we are going to use a superscript I, which I will be explaining very shortly. So, W psi with a superscript I we are writing as 1 upon root over N1 N2, and the summation process will be N1 is equal to 0 to N1 minus 1, N2 is equal to 0 to N2 minus 1, and this will be S N1 N2, and this will be psi J0 K1 K2, psi with a superscript I, and parameters N1 N2. Okay. And the significance of this I is that I can be either the H or the V or the D. What are the significances of this H, V and D? Horizontal, vertical and diagonal. So, remember that, I mean, just a little while back we were using this notation W psi D, V, H. So, D basically means high pass in both rows and columns, V means high pass along the column, but low pass along the rows, H means just the opposite of that. So, that is why totally we have got 3 such versions. So, accordingly we have to apply the filter, that is to say that when we are talking of psi H, okay, when we talk of psi H, essentially psi H will mean that it will contain a low pass filter along the columns and it will contain high pass filter along the rows. So, accordingly the transformation kernel will be arranged. So, this is how you are obtaining from S N1 N2, you are obtaining the wavelet filter, the scaling function filtered and the wavelet filtered images. Okay. You are obtaining W phi and the 3 W psi filtered images. Now, having known this transformation, which we can call as the the direct DWT as applicable on the images. So, this is the DWT in the direct form, and because it is a reversible transformation, we should be able to recover S n1 n2 given this W phi and the 3 W size. What I mean to say is that if somebody supplies to me this kind of a subband picture, okay, that means to say that somebody has provided the individual subband filtered images after applicable after application of the scaling and the wavelet filters along the rows and the columns. Okay, I should be able to get back the image from there. Okay. Now, how to get back that? So, that will be obtained by having an inverse discrete wavelet transform. So, what is the inverse discrete wavelet transform going to yield us? It will give us S n1 n2 out of this W phi and the 3 W size. So, mathematically the inverse DWT, or I can write in short form as the IDWT, inverse DWT expression would be S n1 n2. This could be written as 1 by root over n1 n2. Now, in this case, the convention that is followed is that both for the direct transform and the inverse transform, this 1 by root over n1 n2 factor is used uniformly, so that the direct filter structure and the inverse filter structure, they remain the same, because totally we require a normalization by a factor of 1 by n1 n2, okay, means application of the direct and the inverse. So, depends how you accommodate that 1 upon n1 n2 in the forward and in the inverse. One way of doing it is to have 1 by square root of n1 n2 for both forward and the inverse. So, 1 by root over n1 n2, and then we have to write a double summation, and that double summation would be over k1 and k2 applied on W phi j0 k1 k2 into phi phi with subscript j0 k1 k2 with n1 n2. So, phi being the transformation kernel or the filter, whatever way you talk of. Okay. So, this will be the low pass filtered version, and what we have to do is to add it up with 1 by n1 n2, 1 by square root of n1 n2, and in this case in the summation process there will be not only summation over k1 and k2, but because we have to add up the 3 subbands, okay, we just put yet another index which we call as I is equal to 0 to I could be H or V or D, I could be H, V or D, and summation over k1 and k2, and again one more summation term we are missing over here, that see, this is for one scale that we are obtaining. Now, typically we are going to have a multi-scale filtering situation, like in this case we have obtained a multi-scale filtering. So, essentially what we have to do is to add up over the scales also. So, what we require to do is that although the LL subband part we are doing from the highest subband, and the highest subband if we consider to be the J0, what we should do is that we should have yet another summation term. So, better we rewrite it as plus 1 by root over n1 n2 summation over I, and I could be H, V or D, and then the scale factor we put as J. So, J is equal to 0 to, we can typically write it as infinite, because I mean depends that how many levels of partitioning you have done. So, it is not actually infinite, it will be summed up to the levels of partition that you perform, summation over k 1, summation over k 2, and in this case it will be W psi, of course with a superscript I indicating HVD over j k 1 k 2, j being the running scale, okay, and this multiplied by psi again superscript I over j k 1 k 2 n 1 n 2. Okay. So, if we do that, if we do this entire summation process and add it up with the LL subband, okay, we can recover S n 1 n 2 and S n 1 n 2, it is not S cap n 1 n 2 or S dot n 1 n 2, because we have not applied any quantization. Okay. So, the signal is exactly recoverable, okay, as long as the filter does not do any truncation. Okay. If we neglect any truncation error because due to the filtering, assuming that the filter that we are applying is completely a reversible filter, okay, it should be possible for us to obtain S n 1 n 2 directly without any signal degradation or whatever. Now, what we can do is that, okay, application of the filters. Okay. Now, what type of filters are we using as the phi filter and as the psi filter? Okay. Now, as I mean, it is very clear that we have to apply a two-dimensional filtering over here, and two-dimensional filter can be realized by a cascaded form of low pass filter and high pass filter, right. So, what we can do is that we use two filters. Let us say that if we use H phi of n, okay, and H phi of n will be a low pass filter, and if we take its coefficient as 1 by root 2, 1 by root 2, which means to say that this is a 2 tap filter. If we take a 2 tap filter for H phi of n having coefficient 1 by root 2, 1 by root 2, and as H psi of n, okay, if we take another 2 tap filter which will be having the coefficients 1 by root 2 and minus 1 by root 2, okay. What type of filter is that? Anybody having idea about what filters we are talking of? What is the sketch of the filter? Okay. Here, of course, this is an FIR filter. So, in this case we are having if we plot n over here. So, for n is equal to 0 and for n is equal to 1, we are having value equal to 1 by root 2. Okay. Whereas, so this is for n equal to 0, this is for n equal to 1, whereas for H psi filter for n is equal to 0, we are having a value equal to 1 by root 2, and for n is equal to 1, we are having a value equal to minus 1 by root 2. So, essentially for the low pass filter, what we are doing is that we are adding up, I mean, because it is a process of averaging. So, you apply the filter, this filter. So, the two adjacent samples would get added up, and here what happens is that when I apply H psi filter, the two adjacent samples get subtracted from each other. So, this is just a simple addition and this is a simple subtraction, and in fact, if you remember that this conforms with our definition of the Haar filter. Haar filter we discussed, okay, that Haar low pass filter was, of course, that time we defined on the continuous domain. Okay. So, Haar low pass filter was this. Okay. So, here we were indicating the Haar wavelet or the Haar scaling function to be this, and the Haar wavelet function was, here it will be up to 0.5 and then 0.5 to 1 it will be negative. So, this is the and this amplitude was 1, this amplitude was 1 over here. So, this is 0.1, so this is 1. So, this was in the continuous domain, this was the Haar scaling function, continuous Haar scaling function, and this was continuous domain Haar wavelet function. This is Haar wavelet, that one was Haar scaling. Now, this is just the FIR filter version of Haar scaling. So, this is FIR version of Haar scaling, and H psi of n will be the FIR version of Haar wavelet. Followed my point? So, one can apply this very easily. Okay. In fact, computationally it is a very simple thing. 1 by root 2 is a constant factor. So, you can multiply by 1 by root 2 with every level of scaling you have to do that 1 by root 2 factor of multiplication, but other than that it is only adding samples or subtracting samples. If it is low pass filter, add the samples, if it is high pass filter, subtract the samples. So, conceptually it matches, because any low pass filter would basically mean averaging, any high pass filtering would mean a differentiation, and differentiation in the discrete domain means it is just a subtraction or difference in the discrete space. So, this is what we will be obtaining, and in fact, a still image compression system uses this wavelet in a big way. Okay. And here essentially what we are doing is to analyze the signal into different subbands. Now, so far we have not talked about the compression. So, if we are talking of still image compression, then it must be seen that how this individual subbands, this LL, HL, LH, HH, how individually these subbands can be compressed. Now, there must be some amount of redundant information which will be present. At least prima facie what we can say is that whenever we have got such different subbands, okay, I have already said that the image will be rich in the low frequency content. So, that means to say that LL will contain more information and the other subbands will be having a sparsity of information. I mean, even if we truncate the higher frequency coefficients, just like the way we did for the DCTs also, because DCTs, although the motivation was a psychovisual motivation that was applied, and that was the main reason for truncating the high frequency coefficients in the DCT. Even in wavelets also the high frequency coefficients could be I mean quantized more severely or quantized more coarsely as compared to the I mean the low frequency signals. Okay. So, in order to make effective use of the compression, what we should do is that we should study that what is the interrelationship between the different subbands. Is there any interrelationships? Is there any spatial interrelationship? That is what let us study. Let us say that we have only the first level of partitioning. So, this is the, So, this was the original image and we have got 4 subbands LL, LH. Now, let us say, I mean, I just wanted to draw it by using the grid of this paper. I think you should be able to locate the individual grid positions in this picture. Now, let us say that if I pick up any square within this, say I pick up this one and it is a pixel, let us say. So, which means to say that the original size of the image was how many? 8 by 8 pixels. Okay. So, 8 by 8 pixels was the original array. So, original array was 8 by 8 pixels, and now I have got 4 subbands. So, individually each subband now contains an array of 4 by 4 pixels, right. Now, this is a 4 by 4 and let us pick up any particular pixel. Let us say that this is the pixel that I have picked up in the LL subband. For simplicity, I have assumed only the first level of decomposition. Now, spatially a position that is picked up over here, which means to say that in terms of the image coordinate within this LL subband space, if I take this to be the reference, then within the LL subband its coordinate is 1 1. So, this is the 1 1 coordinate with respect to the LL subband. Now, at the same position, at the same pixel position 1 1, okay, we are having the HL subband image. So, HL subband image will be having this pixel position. The corresponding pixel position in the LH will be this and the corresponding pixel position in this will be this. So, that I can say that this pixel is related to these pixels in the sense that this pixels higher frequency versions or higher frequency coefficients corresponding to these pixels are available in this HL, LH and HH subbands, right. So, there is a relationship that this is as if to say related somehow to this. Now, let us see that what will be the state of this relationship when we have more levels of partitioning. Let us say that when we have 2 levels of partitioning. So, in that case again I try to draw the same type of a grid. This is after the first level of decomposition and we make a second level of decomposition. So, now individually these subbands are having 2 by 2 pixels. Let us say that I pick up this pixel from the topmost LL subband. So, this will be having some correspondence with this, means its higher filtered versions would be this in the corresponding, I should call as HL2 now. This pixel would be what we will be getting at HL at LH2. This is what we will be getting as HH2. Now, this must have some kind of a relationship with these subbands also. But now see, if we call this as LL2 and we call this as HL2, right. This we are calling as LH2 and this we are calling as HH2. Now, look at HL2 and look at HL1. This is HL1, this is LH1, this is HH1. Now, if I ask you that find out a correspondence of this pixel with the corresponding pixels in the HL1 subband, you have a difficulty. Why difficulty? Because here the resolution is a 2 by 2, this is a coarse, whereas here we are having a resolution of 4 by 4, this is a much finer resolution. So, 1 pixel in the HL2 subband corresponds to how many pixels in the HL1 subband? 4, because the resolution is higher in this. So, what you are seeing as 1 pixel in HL2 will be 4 pixels in HL1. Okay. So, this corresponds to 4 pixels over here. Similarly, this HH2's this pixel would correspond to 4 pixels in HH1. 1 pixel in LH2 will correspond to 4 pixels in LH1. Okay. And LL2's pixel is already related to these 3. Now, in this form, what emerges is a kind of a data structure representation. What we can do is that if we take this pixel, 1 pixel in LL2 subband as a starting point, then we can consider that its corresponding pixel in the HL2, LH2 and HH2, these 3 other subbands, its corresponding pixel positions will be considered as its descendants. Individually, each of these pixels will be having 4 descendants. So, HL2's this pixel will have 4 descendants over here, this will have 4 descendants, this will have 4 descendants. This is a picture that I have drawn with 2 levels of decomposition. If I draw it with 3 levels of decomposition, in that case 1 pixel in HL3 would correspond to 4 pixels in HL2, and every 1 pixel in HL2 will correspond to 4 pixels in HL1. So, which means to say that 1 pixel in HL3 would correspond to 16 pixels in HL1. So, there is a tree that evolves, okay, which means to say that pick up any pixel from the topmost LL subband. So, consider any pixel from the topmost LL subband, let us say that this is LLN. LLN will be the root of this tree, will be at the root of this tree, and will be having its descendants in HLN, LHN and HHN. Now, every pixel in HLN will be having 4 descendants in what? In HLN minus 1. HLN minus 1, it will be having 4 descendants. LHN will be having 4 descendants in LHN minus 1. HHN will be having 4 descendants in HHN minus 1. Individually, each one of this will be having 4 descendants down in the HLN minus 2 or LHN minus 2, HHN minus 2, like this. Okay. So, this is a kind of you can say that parent offspring relationship, okay, if you call this as the parent, okay, and this is called as parent offspring relationship between the pixels, or you can also call it as, I mean, some literatures describe this as ancestor descendant relationship. Descendant relationship. So, at 3 levels of decomposition, you can say that this is the grandfather this is the father and these are the children, like that. Okay. So, this is how the tree a tree structure evolves, and why this tree structure is efficient for encoding the wavelet coefficients. Okay. I will discuss that in the next lecture, okay. And that will give you some insight as to how the wavelet coefficients are encoded. Okay. Thank you.